This piece of code demonstrates the way a linked list would typically be used inside a C program. So in that previous example, we were constructing this linked list out of variables in main. But I mentioned at the end, that's fine for learning about structure, but that's not the way we should really be doing this, because we want to construct a list with as many nodes as we need, which means I should be able to create nodes on the fly. So we might come up with a structure like this. First, I'll make this a type called linked list. I create a list called L1, and what we'll notice in a couple of minutes is really these linked list objects are actually just surrogates for this head pointer. So all they really store is just this head pointer, but by wrapping it up in an object of type linked list, that makes it easier to pass it around between functions. And so we begin, if we create a brand new list, we'll set up our list to be empty initially. We're not going to move our code around though if we can avoid it. And so that means the head pointer points to null. And I'll create the second linked list object L2, and then I'm going to call some functions. And so our goal in this video is to write these functions. So the add to front function takes a pointer to one of our linked list objects and adds a new element as the first element of the list. So if we update what we have over here based on this line, what we should do is we should update the list to contain 6 as its first element. All right. There's the 6, and then the next node after the 6 doesn't exist, and so it points to null as its next node. All right, so then we add the element 10, and so what we would do here is we would splice in the value 10 before the element 6, and so we would make a new node to contain the element 10. We would redirect these pointers, and then I guess 6 would actually still be at the end of the list. So notice that because we're calling add to front at each step here, we're sort of constructing the list in reverse. And then to complete that, I want to add the element 17. So we make a new node, and then we adjust our head pointer to point to our new first node, which will now be 17. And we have the node containing 17 to point to the node containing 10 as its next pointer. And so if we now traverse the list, we start at the head pointer, we get 17, then 10, then 6. So notice that if I add elements to the front in order, they're going to come out in sort of the opposite of what you'd expect. The 6 ends up being the very last element of the list because I add the 10 before that and the 17 before that. Down here, we use this function add to end, which adds elements at the end of the list. And although, unlike an array, we don't have limitations on the size of the list, and we can splice stuff in anywhere, it does turn out that add to front is a bit easier to write. Because since, I guess I should redraw this, since when we're working with a linked list, all we ever really have on hand is this head pointer, it's pretty easy to add something between the head pointer and the first element, whereas adding something at the very end after the last element, so this is, whoops, I fell for my own trap here. So let's see, it's 10, 17, 10, 6. So if I have this list here and I want to add something at the very end, like add the number 100, what I have to do to add that is obviously I have to make a node with the value 100 in it, but I also have to go find where the current end of the list is, because I need to reconfigure where this node points to. So here what I would do is I would adjust the next pointer off of the 6 to point to the 100. And then the next line adds the element 200 at the end of the list after that. So we get a configuration like this. And then we print it out. So of course, we're going to need a function to print our list, or else we'll have no way of actually knowing whether any of the code that we write to add nodes ended up working. Now, for the sake of our list L2, we'll use a loop to add a whole bunch of elements to it. And we could easily extend this loop to go up to 100 or something, just to verify that we can add literally as many elements as we want to our lists. And finally, something we really have to make sure we write, even in this first part, we need the ability to delete the nodes that we create. Because it turns out that what we're going to have to use to create these nodes on the fly is the malloc function. And we know that when we call malloc, we have to make sure that we then later call the free function to deallocate that storage. So what we have to do is delete each of the nodes of the list that we have at the end. And it's worth considering if I write a function to just delete the very first node, so that would be doing conceptually something like this. If I want to delete the first node of what I have here, what I would do is I would reconfigure the head pointer to point over here, and then I would deallocate this node. You might notice that if I do that, if I have some code to deallocate the first node, I could just call that over and over again to deallocate every node. I keep going until we're back down to an empty list. So I have to do all of those parts. I want to add nodes at the beginning and at the end. I want to print out my list, and I want to be able to delete the first node of the list. And in the next video, we're going to talk about writing some functions that work with processing lists. So once I have a list, what interesting things can I do with it? Things that'll take us back to the early days of the array stuff, like being able to add up all the elements in an array or in a list, being able to find the maximum, things like that. So let's start with going over, I guess, the machinery we have. So we've got our node type called node, and I've taken to calling the element, I'm going to call it value to differentiate it from the node itself. The word element can sometimes be, I used in the last video, I kept saying element when I actually meant node. So to avoid that confusion, we'll call it value. I've also defined this structure called a linked list. And you can see it's a sort of useless struct type. Why would we have a struct type with only one member? And the idea is that I want to be able to give the entire representation of the whole linked list to a function. And I want the function to be able to modify it. When we add something to the front of our list, the function that adds that node will be modifying our head pointer. So I want to have an easy way of passing my linked list around the program and giving other functions the ability to modify my head pointer. It's true I could just pass in the head pointer directly to the function, but if I want the function to be able to modify it, I have to pass a pointer to the head pointer, and that would require using 2 stars. So I think a nice humane alternative is to create this object of type linked list and pass a pointer to that. All right, so first, print list. And I know we haven't created a list yet. We haven't actually added any nodes, but we should, based on what we know about lists so far, still be able to iterate over a list, to write code that iterates over a list and prints out each element. So just like in the previous video, I'm going to start by creating a node. I will start by drawing a little diagram to remind myself what I want. So I'll add, I don't know, we'll just make my usual list here. So if I have a list like this, and this is my head pointer, what I want is the ability to walk through the list from start to finish. And so I'm going to need some extra pointer to keep track of what node am I currently working with. So notice how my linked list object L is passed via a pointer. So I go into the list object and I get the head pointer. There we go. And I'm going to, just like in my previous video, I'll use this extra pointer here to denote what my current node is. So I start by setting current to equal head. So current will now be a pointer to the very first node in the list. And then what I want to do is I want to keep walking through the list as long as current isn't a null pointer. So while current node is not equal to null, I want to keep walking, and as long as current node is not equal to null, that means that my pointer points to a valid node. So I can go in and ask for that node's value. So I'll print out the value in the node. We are making a list of integers here, so I'll print it with %d, current node arrow value. And then when I'm done, actually I'm not done, before I continue, I have to make sure that I increment, that I adjust my pointer to point to the next node in the chain. Once I'm done with this node here, I want the current pointer to be adjusted to point to the next node. So I go grab the next pointer from the node I'm currently looking at, and I set my current pointer to be whatever that is. So current node equals current node arrow next. And just like in the previous video, observe that if I keep walking along that way, current will first point to 10, then it'll point to 17. And when I'm pointing at this and I'm done printing this out, what I will do is I will say current node equals current node arrow next. Well, the next pointer of the node I'm looking at is a null pointer, and that means that when I finally reach the end of the list, my current pointer will be a null pointer. And that's why this loop condition is helpful, because it means the loop will end as soon as I walk past the end of the list, and current is a null pointer. Okay, when I'm done with that, I will print out a new line. All right, so I have no way of testing this function. I mean, I hope it's correct. I have no way of testing it because I need to be able to add stuff to my list first. I think, though, if we go back down to main, maybe we can see that I should be in a position to test the function if I stop here and I write add to front. So I'm going to comment all of this out. Once I have add to front working, that'll be just enough to get me a list that I could print out. It's worth considering, just like usual, I should probably be doing more testing than I will be doing in this video. I should make sure, for example, I can still print out empty lists, or I can print out lists that have only one element. But for now, we'll suffice to do this, and maybe as an extra exercise, go right ahead and do whatever extra testing you think is necessary. So I have print list, or I have what I hope is print list. I will verify that I can compile it, because at least then I'm not, there's no obvious things to fix. So these two complaints in main, well, this complaint in main is just that I'm not using one of my variables. The delete first function hasn't been written yet, so I guess it makes sense that I'm not returning a value from it. So now add to front. And if you're asked to write code that does something like this on an exam, make sure you've drawn out a little sketch of a list to think about what you have to deal with. And also always consider that when I'm adding nodes, I could be adding to a list that's currently empty. So I'm actually going to make myself two little sketches. Okay, so at the top, I have an example of a list that has stuff in it. And here, I have an example of a list that is empty. A list can be empty. A list can have 0 elements. And that'll happen when its head pointer equals null. So what I think I should do here is, I don't know how I'm going to differentiate between these two later in the game. So maybe what I'll do is I'll just do a test at the very beginning. I'll say, if I'm looking at an empty list, do something different. So let's see. If L arrow head, so if the head pointer of my linked list object is equal to null, then I'm adding an element, adding the first element to an empty list. Else, adding an element before an existing node. Okay, so I have two separate cases here. Maybe as I go forward, I'll notice a way of merging them together to some extent. But really, when you're working with lists, it is often helpful just to divide up, to break things up into cases, and then write the code for each case and see if you notice any similarities. So let's start with this. What do I have to do to insert a new node into the beginning of this list? I can think of a couple of things. So first, what I should do is probably make a new node. Certainly I need to do that. So let's make a new node. What is it? I don't know, 187. Okay. I need to make a new node. I have to make sure that that node has a valid next pointer. Well, wait, if I'm adding an element to an empty list, well, then I guess there is no element after it, so its next pointer will just be null. Okay, and then I need to make sure that there's something pointing into my new node. In general, when you're working with what we call a singly linked list, like this one here, where all the arrows point in the same direction, if you make any adjustment to the structure of the list, you should expect that 2 pointers need to be set. You need to set the pointer pointing out from your node, and you need to set a pointer that points in to your node. So I've already created my node, added a value, I've set the next pointer to be null. Now I have to set the pointer that points in. And of course, because the thing I'm adding will be at the beginning of the list, what I want to modify is the head pointer. Okay, so those, I now have a set of steps. Create a new node. Set the value of the new node to new element. That is this element that I have been provided as an argument. Set the next pointer of the new node to null. So remember that if I create a new node, I should expect that the contents of that node are garbage, and that means I need to set that next pointer myself if I want it to be null. And then set the head pointer of the list to point to the new node. Okay, this is my shopping list. And we'll worry about what to do down here once we've gotten some practice with this case where the list is empty. Okay, first issue, how do I create a brand new node? So what I want is to, whenever this function is called, make up a brand new node object out of nothing. And in particular, I need that node object to survive when the function ends. So it wouldn't be sufficient to write something like node, new node. I mean, sure, this creates a node, but it's a node that's scoped inside of this function, which means the node will be deleted when the function ends. I need the node to still be chained into the list once the function is over. I want the node to live forever until I delete it. So what I need to do is break the usual rules of scope, and that means I have to use malloc. So what I'll do is I'll use a node star because malloc only ever returns a pointer. I call malloc, I say, I'd like some space for a new node. Well, how much space do you need? Well, I guess I need as much space as it takes to create a node. So I'm creating something of type node, so I'll ask what is the size of a node, and I'll ask malloc to please give me that amount of space. And then I will take the pointer malloc returns, and I'll call that new node. Okay, so that's a node star, so I have to keep that in mind. Now, new node arrow value will be my new element. So the element that I've just received from the caller to the function. Maybe as I go, I will follow along on the diagram. So where we are right now, as of this step, is our list is empty. I just created this brand new node. There it is. It's all nice and brand new and shiny. Okay, and I've just added my element to it. So I have to put something in here. So I'll put in 187 just for the sake of having a number. Now I set the next pointer of my new node to null. So new node arrow next is equal to null. All right, so now I've got this situation happening. And then finally, I adjust the head pointer of my list to point to my new node. And keep in mind, if you try and walk through these steps without having a diagram, it will make very little sense. I don't know if I'd be able to write all these steps to reliably do all this stuff without having a diagram sketched out on the side. So the head pointer in my linked list object, that would be of type node star. And so I have to check whether I can do this assignment. So this expression has type node star. My variable new node also has type node star. So I can do the assignment. And the adjustment that I've just made is equivalent to the diagram that I have here. So there we go. My head pointer now points to 187, and then 187 points to nothing because it's the only node in the list. So I think I've now done this case. So what do I have to do if I add an element before an existing node? So I'll clean this up a little bit. There we go. And then, oops, I guess I lost that. So to add an element before an existing node, here are the steps I have to map out. First, I obviously am going to have to create a new node again. So there's my new node. It's brand new. So create a new node. In fact, I'm actually going to cannibalize some of these steps. You know, okay, you're all smart people. I'm going to copy and paste my shopping list, and maybe it's obvious that that means I should copy and paste the actual things that I do. I'm going to need to create a new node. Okay, so we'll just keep that code. We don't have time to waste here. Okay, I need to set the value of my new node to my new element. So I'll do that. So this step was pretty much the same in both versions. Okay, so what do I do next? Well, I already have some elements here. I already have some stuff in my list. So it wouldn't be appropriate to set the next pointer of the new node to be null, because the point of this function is to add my new node at the beginning of the list, add it here. So what I have to do is I have to set the next pointer of my new node, set the next pointer of the new node to the current first node in the list. Okay, so how do I get a pointer to the first node in the list? Well, I have one. It's the head pointer. So I need to say something like new node arrow next is equal to the current value of L arrow head. Okay, so then I end up with L arrow head points to this node, so I end up with this situation. All right, and then finally, I have to set the head pointer of the list to point to the new node. Okay, so that gives me this situation. Once I'm done, I will have this. Just like before, the new node I create will become the head of the list. So L arrow head equals new node. One thing to observe, as I said with the diagram earlier, even if you know these are the 4 steps you have to follow, it's really easy to accidentally try and do this one second instead of doing this one and then this one. If you have a diagram, it's much more difficult to make that mistake. For the sake of argument, though, let's see what happens if I accidentally tried to do this step first. So I'm gonna rewind my diagram here. There's no undo button on my screen drawing thing, so I just have to do this manually. All right, so suppose I'm back at this step. I've just made my new node, and there it is, it's got an element. So then I say, okay, now set L arrow head to point to my new node. Great. Now I say, set the next pointer to point to the current first node in the list. So I want my new node to point to this node here. But wait a minute, nobody has a pointer to this anymore. It's lost at sea. I've lost the entire rest of the list. It's become untethered and it's slowly floating away. So because I had a diagram, it was easy for me to map out the steps, and it's easy for me to catch this mistake before I make it. I noticed that I can't redirect the head pointer until after I've set this next pointer. So we'll erase this. And maybe that helps to prove why having this sketch makes it really easy to not only know the steps, but actually to get the steps in the right order. So here, if the head pointer still points here, the next thing I do is I set my new node's next pointer to be the head pointer for the list. Okay, that works fine. So, So the rest of the list is still tied down. It's now attached to my new node. And now if I redirect it, everything is still tethered together. If I don't, I lose everything else in the list, which is not only going to ruin my list, it's actually going to be a bit of a catastrophe from a memory standpoint. Because if you lose the very last pointer to the beginning of a long list, all of the nodes in the list are now lost forever. Not only can you not use them, you can't deallocate them. That memory is now leaked. It's wasted. And so it's very important that we always keep pointers to things. And we'll come back to this in a few minutes when we talk about deleting a node. Okay, so I think I've now done all the steps I need to add the node if the list does have stuff in it. So one exercise to think about for later, when you take a look at the posted code, is it turns out you don't actually need this if statement. You could actually do exactly the same these four steps in both cases. And the thing you should observe is the only difference between these two sets is this. On this version, where the list already has stuff in it, I set the next pointer to be the head pointer. Up here, I set the next pointer to explicitly be null. But what's interesting is, in this version, the head pointer is actually null. So if I were to just run these four statements, it would actually be identical to what I had above. Now that said, that doesn't mean that it's a bad idea to write it this way. It's often really helpful in linked list programming to break things down into cases like, is the list empty versus does the list already have elements? So I'll leave that. I think this code should work. Famous last words, obviously. Let's take a look. So first, these warnings are still innocuous. They're just working with functions that we haven't written yet, or bits of input, bits of test variables that we haven't used. So right now, all I have is I'm adding three elements, 6, 10, 17, such that the list will end up being 17, 10, 6, and then I'm printing out the list. And there they are, 17, 10, and 6. Okay, so obviously add to front might need a bit more testing, but being cautiously optimistic, I'm going to try writing add to end. We're going to discover that add to end is actually pretty complicated. It requires us to do two things. It requires us to combine the logic that we've already seen with print list with the logic from add to front, because I need to not only be able to add a new node, I have to first find the end of my list. So we'll try writing add to end, and that'll allow us to uncomment this other bit of testing code, which does also test print list a little bit more, and then we can add a couple of other tests to add to front later. So I'll save this, we'll go up to add to end. So what I want to do here, I give you a new element, and I want you to create a brand new node and install that node at the end of the list. And just like before, there are two cases. What if the list doesn't have anything in it already? And we might observe we do sort of have a way of cheating here. So what if the list is empty? If L arrowhead is equal to null, which means there are no nodes in the list, wait a minute. If I'm looking at this list and I want to add to the end, I want to put a new node here. But isn't it true that if the list is empty, then adding to the end of the list is the same as adding to the front? Well, yeah, it's going to be the first and last element. So I'm going to sort of pull a dirty trick here. If I notice the list is empty, I'm just going to call add to front. Trust me on this. So because the list is empty, the element I'm going to add is going to be the same element that I would add if I added to the beginning, because the beginning and the end are the same place in this list. And because I don't want to have to do any more linked list writing or pointer code than I possibly have to, I'll just call my other function, the function I already tested. Okay, so that gives me an easy way out of that problem. And of course, if this were an exam question, you could write the 4 assignments. That's also valid. It would be these same 4 things, the logic we already went through earlier in the video. Otherwise, what do we do? Let's write a comment here. Adding to the end of an empty list is the same as adding to the front. Okay. Okay, in this case, adding an element after the existing contents of a non-empty list. So here what I have to do, in this case, I know that the list is non-empty, because if I'm in the else, it means the list has at least one element. That means that I don't actually care. Let's draw a more conceptual diagram here. So I don't care exactly how long the list is. All I care is that there is some last element. I shouldn't even call it an element. There I go again. Some last node. There's somewhere in the list there is the last node of the list, and we know that it points to null. And the key thing about this case is there is going to be a last node. We already handled the case where the list has no nodes, so there will be an actual node at the end of the list. What I want to do is go find it. I want to find that last node, so I should actually make a variable to store a pointer to it. So I want to make a node star last node. Actually, I'm going to say old last node, just because we're obviously about to add our own new last node at the end of the list. So I find the last node. I go make a new node with my element in it. So I will make a comment for that. Create a new node. The indentation's messing up because of this funny assignment statement. I'm just going to do this. Create a new node. Set the element in the new. Actually, you know, we're all pretty savvy. We know that these two steps are probably going to be about the same. So I want to create a new node, and I want to set the element stored in the node to be the element I was provided. Okay, that part is similar. Now, the node that I'm adding to my list is about to become the new end of the list. I'm adding at the very end of my list. So the next pointer off of this node will always be null. Okay, so set the next pointer of the new node to null. Okay, now we'll put that on pause and come back up here. I'm going to go at some point find the old last node, the current end of the list. When I find that, I'll end up with this variable that has a pointer to this last node. That means that when I need to install my new node, what I need to do is, well, let's see, I've already created the node, I've set its element, I've set the next pointer, but I should expect that there are two pointers I have to modify. Something points out and something points in. And so what I want to do is I want to set the next pointer of the old end of the list to be my new node. So I want to end up with this situation. So then we'll go back down here and we'll say, okay, so set the previously last node to point at the new node. I'm going to say set the next pointer of the previously last node. Well, that's a mouthful. The old last node, that's a little bit better, to point at the new node. Okay, so I have this pointer called old last node, and that arrow next is going to equal my new node. Okay, so this is all I have to do to set up my new node. But the problem is, before I can do that, I have to find the current end of my list. So I'm going to just delete this part of the diagram, and we'll talk about this sketch here. So the question is, I know how to go from the beginning of the list to the end, but I want to stop. I want specifically to stop when I have a pointer to the very last node in my list. There are a few ways of doing this. One of them is you could use the same loop as print list, which steps through the entire list one by one. But you have to be careful because at the end of this loop, at this point, the value of current node is just equal to null. I want to stop one step sooner. I want to stop just before we run off the end of the list. So I'm not going to copy and paste the loop. I'm actually going to make a new loop from scratch. So old last node. Well, here's what I'm going to do. Here's my logic. I'm going to begin by saying, okay, the last node, at the moment, I don't know where the end of the list is. So I'm going to start by assuming the end of the list is the same as the beginning. And we'll work on that. So I'll say, let's begin by assuming our last node is the beginning of the list, the head. And now what I'm going to do is I'm going to keep walking through the list until I actually reach the end. But then the question is, wait, when am I looking at the last node? Okay, well, what distinguishing characteristic does the last node in the list have? Okay, so here's the first node, it points to something. Okay, fine. Here's the second node, it points to something. But yeah, wait, here's the last node. Its next pointer is equal to null. That's its definition. The last node of a list always points to null. So what I could do is I could keep walking until I hit a node whose next pointer is equal to null. In other words, I say while my old last node, well, its next pointer is not equal to null, well, then I clearly am not looking at the last node. So I just walk along. Old last node equals old last node arrow next. Let me try walking through this logic. Okay, so I start by setting my last node to be the head pointer, to be the first node in the list. And I know, because I'm in this else, that there is at least one node in the list. So this is not going to be a null pointer. Okay, so then I'm going to run the loop. I ask the question, look at the last node. Is its next pointer equal to null? And the answer is no. So it is true that it's not equal to null. So I walk along. I set the last node to be the next thing. I ask the question, is this next pointer not equal to null? And the answer is, yeah, it is definitely not equal to null. So I keep going. I reset the pointer to point to the next thing. Then I ask the question, is it true that this node's next pointer is not equal to null? And the answer is no, I'm afraid it actually is null. And so I stop. And so as of line 89, I should expect that last node will point to the very last thing in the list. Okay, so there's a lot going on here. And I mean, if you look at it in terms of lines of code, this isn't actually that many lines of code in the grand scheme of things. Compare this to assignment 5 or assignment 6. And if we strip out the comments, there really isn't that much going on. A loop and a bunch of assignment statements. But there's a lot of nuance to it. And having the diagram on hand is really saving us here from just running off and writing a bunch of weird random stuff that results in the program crashing. So we'll try this out. I guess I better make sure in main that I've uncommented the right stuff. Okay, so I should expect to see 17, 10, 6. That's this print statement. And then I want to see if I can add the element 100 and then 200 to the end of my list. And then I'm going to see what happens if I add all these squares to this list L2. Okay, we'll try that out. Here, this warning is still something we don't have to worry about just yet, and we'll try running it, and we'll hold our breath. All right, 17, 10, 6. These are the elements that were added by add to front. That looks good. I then add the element 100, and then I add the element 200 to the end of the list. Okay, there they are. And then I construct a new list by calling add to end inside a loop. And the key here is, you can try this yourself, you could call this as many times as you want. Each time it synthesizes a new node object with malloc and then tacks it on to the end of the list. And so, even more importantly, I now have two separate linked lists in this program. Two completely independent linked lists that are I'm adding elements to independently and printing out. But I have one thing left to do in this video, because for completeness, we really need to make sure that this gets done. So I need to make sure that because I've allocated all of these nodes using malloc, that it's obviously pretty important that I deallocate them, that I call free. So I'm going to redraw my diagram here. Okay, so suppose I have a list like this. Okay, the first thing is, if I can delete one element, then I could, if I want to delete every element, just run a loop that keeps deleting elements until the list is empty. So we know a list is empty if its head pointer is equal to null. So what I'll do, if I want to delete everything, is just delete the first thing over and over again until there's nothing left. So that's my way of avoiding having to write too many extra functions. But I still need a function that deletes the first element of my list. So here it is, delete first. And I'm going to write this the way that we typically write these functions. Even though we don't need the return value, we are going to need it in the next video, or we could need it in the future. So typically when you write a function to do deletion, it is actually relatively common that the function will delete the node, but return the value stored in the node, because maybe you wanted it for something. And because obviously once this function is over, that node is gone forever. So maybe in case you wanted the element that was in there, it'll return that element to you. Okay, so what do I need to do here? And the difficulty is I have to be very careful when I call the free function. Because, I mean, maybe it's obvious. If I wanted to delete the first element of this list, well, yeah, okay, it's this one, whatever the head pointer points to. But it wouldn't be acceptable to say, okay, I want to delete that first element, great, let's just free the first element of the list. If I do this, I have a real problem, because deleting the first element isn't just getting rid of the node, it's also reconfiguring the list. I want to make sure that when I'm done, the head pointer points to the new beginning of the list, which is the 10. As soon as I call the free function on a node, that node becomes invalid forever. And that means if I need a pointer to the 10, I can't use the pointer stored in the node after it's been deleted. I have to make sure that I've squeezed all of the information I need out of this node before I call free. Because once I call free, it's gone forever. So I've got to refine my approach. And the way I'm going to do this is actually pretty straightforward. I'm just going to say, okay, so here's my list. I want to delete this node here. But before I delete it, I'm going to completely disconnect it from the list, which means I have to have something to keep track of it. So I'm going to call this, I'll make a secondary pointer called delete node. Okay, and I'll have that point to the node that I want to delete. And we know already the node that I want to delete is the first node in the list, so I'll call node star delete node equals L arrow head. I'm going to write a quick note here. In the posted version I'll do this, but I'll just say to do. Check if the list is already empty. You could argue that nobody should be calling this function to begin with if the list is already empty, but if they do, I suppose we should throw an error or something and print an error message if so. So it really isn't a problem if anybody's trying to delete an element from a list with nothing in it, because that'll create a real problem. Create an error message and exit the program if so. I'll put that in the posted version. It's not actually that interesting, but just so that you know that I'm aware of this potential here. I am conscious that could happen. So I create this pointer called delete node and set it equal to the current first node of the list. The reason that's helpful is now I can completely detach this node from the list before I do anything else. So what do I do next? Well, what I want to do is I want to redirect the head pointer to point to what will be the new beginning of the list. I want to do something like this. So head now points to whatever the first node points to as its next pointer. So the second element is about to become the first element. In other words, the new head of the list will be the element I'm about to delete, or actually, sorry, the node after the element that I'm about to delete. All right, so I've done that. And you know, for extra certainty, I could even deliberately set the next pointer to be null. I don't actually have to do this. This is optional. But if you look at the diagram, it does really help you sort of believe that you've completely detached your node. Now I've got my list, head 10, 17, and I've got this node floating around in space, completely independent of its surroundings. Now it can be deleted, except for one other issue. But let me just show off what I mean here. So here I can now call free delete node. So I can say, here's this node I have that I previously allocated with malloc. I'm done with it. Please dispose of it. The problem is, I do still need to return the element that was in that node, in this case, the number 6. And I can't write return delete node arrow value. That is, so no, I can't do that. Because once I have called free, I am never supposed to use this object again. And that means that if I still need something from it, I have to save it in advance. So I'm going to call this int return value equals delete node arrow value. So of course, if you ever try and work with an object that's already been freed, that is considered to be a serious problem, and you can expect to be punished severely in the marking if you do that on an exam question. So now I return return value. It looks sort of ugly. I don't like calling my variable return value, but there it is. So I save the number I'm going to want, and then I call free, and I guess for the sake of our diagram, free is doing this. It's gone. I mean, we don't know what's there anymore. It's now undefined memory. We can't use it again. And then I take the value I had saved on the side, and I return that. So that's delete first. And I suppose we owe it to ourselves to do at least one other test of that. So before I run these loops that delete everything, let's see what happens if I delete one or two elements and then print the list out after that. So we'll try this test. Okay, so I delete an element, I print the whole list, I do the same thing again, and then and just to make sure that I'm able to delete individual elements and the list is still intact when I'm done. Okay, so here is where the last test finished, this line here, that's that list of squares, and I then delete one element from this list at the beginning, and notice that there it is, 10, 6, 100, 200. So I did successfully remove that first element, and then I remove the first element again, and now it's just 6, 100, 200. And then down here at the bottom, there's no print statements that show us what's happening here, but I'm using these loops to then delete any remaining nodes to make sure all of that memory can be reclaimed. So in the next video, I'm going to talk about writing some functions that process elements of the list and do a bit more deletion, things like deleting the whole list, so wrapping this loop up in a function, because you'd think that would be a good thing to have. And we can begin talking in future videos about maybe other interesting ways of traversing a list besides just using loops.